Hello and welcome to another video. In this video we're going to be going over the problems from the weekly contest 397. And I didn't have a chance to finish the bi-weekly contest, maybe I'll get around to that, but I'll post these. So in this one, you're given the permutation difference between two strings. And basically they tell you that you have two strings and every character occurs at most once. And one's a permutation of the other. And so they're basically two strings, one's a permutation of the other, and they tell you get the permutation difference, and the permutation difference is for every character, what's the difference in location, what's the absolute value of difference in location. So they show you like here A is at location 0 and it's at location 1, so there's a difference of 1. B is at 1 and 0, so difference of 1, and C is the same, so it's 0, so you should return 2. And then for A, B, C, D, E, here A is 0 and 3, so that's 3. Here it's 1 and 2, so that's 1. Here it's 2 and 4, so that's 2. Here it's 3 and 1, so 2, and so on and so on and so on. So basically, all you have to do is just get the location in the first one, get the location in the second one, subtract them for every single character, and return it. So pretty easy. I made a dictionary for the locations of the first one, and then for the second one, I just calculated them on the fly, but it doesn't really matter. Like, anything kind of passes. Yeah, I noticed for these easy problems, like, honestly, if you've been doing contests, like, for the most part, I can do most of these in like 2 minutes or something. So I think they are a little bit harder than like the standard LeetCode Easy or something. At least some are. But for the most part, you should pretty much be able to do it almost right away. And then I also noticed the second one is also not that bad for these contests. You should be able to do it pretty quick. So in this one, you have a dungeon and you have a magician standing in a line. And a magician has an attribute that gives you energy. And basically, so whenever you go on an index of a magician, you either gain or lose energy based on that number. And you can start wherever you want, but wherever you start, you have to be jumping k jumps at a time. So let's say I start here. I have to go here, and then I have to go like here, and so on. Return the maximum possibly energy you can gain. So in this one, this is also pretty... There's basically one thing you have to recognize, so let's actually ignore this. So let's just draw an array here. So let's say we choose to start, like let's say k is 3. And we choose to start here. Like let's just say we have to start at a multiple of 3 to make it easier. So let's say we have to start here, 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 or here. And let's give it some numbers. So let's say it's like 0, 3, 6, and then like, I don't know. Actually, let's do it this way. Let's do 3, -6, 3, 3. So technically you can start at any one of these, but if you start at 1, then you'll have to jump to the rest. If I start here, I'll have to jump like this. If I start here, I'll have to jump like this. If I start here, I'll have to jump like this. So this is basically, if you can recognize, this is basically Kadane's algorithm. So you can just go through all of these and then add them up, and then if there's like a better thing, then you take that instead. So what that would look like is we'd have like 3 here, and then here we'd have -6, so we'd have a total of -3, which is better than -6, so we're going to keep both of these so far. Then here, if we just start here right away, we'll have a total of 3, or if we kept the whole thing, right, like if we keep a cumulative sum, like our cumulative sum would be -3 before we get here, right? So here it's positive, here it's -3, which is still better than -6, but here our sum is actually 0. So we're just going to say, well, if our sum is 0, then we're just going to want to start here because that's better than taking the cumulative sum. So we start here, and then here we have a sum of 6. So we are going to keep that. So you basically just do Kadane's algorithm, and you have to get to the end. So that's how you do it. Like if you have to start at, if you have to start only at these locations. But what happens if you can start anywhere in the array? So anywhere in the array is also kind of similar, but you can basically just loop from only starting indices that interact with each other. So for example, like this will jump to this, to this, to this. Now if I start at 1, 1 will loop with 4 with 7, and then 2 will loop with 5 and 8. So you can basically start at every index that's less than k, and then do this, and then that will give you actually an O of n thing, because if I start at, like I said, if I start at 0, then I do this. So I visit 4 cells. If If I start at 1, I go here and here. I visit 3 cells. If I start at 2, I go here, and I visit 3. So I visit 4, 3, and 3, and that would actually give you O of n runtime. So essentially, you start with every cell that's less than k, and you do the Kadane's algorithm from that cell to the end. And then whatever like gives you the best is your answer. So if we actually go back, they tell you that you want to start at magician 1. So let's say we start at magician 1, and our jump is 3. So we basically get this, and we'd get 3. And then for this one, we start at magician 2, so we just start over here. But yeah, it's basically just Kadane. So here it is. So I start at every index from 0 to k, and then I jump from that index to the k index after that, and I literally just do a Kadane here, where I just get my total sum versus just taking that one item. If that one item is better, I'll say let's start here instead. And then once I'm done with all the jumps, once I'm actually at the end, because you have to actually get to the end, then for that start index, I just record the best place, or like what my result was. So that's basically it, and this is going to be O of n. So pretty simple. Let's go to the next one. So here, you have a matrix of positive integers, and you can move from any cell to any other cell. So essentially, let me use this in a picture. So we can start anywhere we want, and we can move anywhere we want, but the criteria is we can only move right or down, but we don't have to move one cell at a time. So for example, we can go like here, we can go here, and so on. And you have to make at least one move, and they tell you like what's the best score you can get, and the score is basically, if you start at num1 and go to num2, it's just num2 minus num1. So for example, if I start here and go to here, and actually, can I do that? I think I can. Let's see. Yeah, so I think you are allowed to make like one move. Let's see. I think you are allowed to make a move like this, where you start at 9 and move to 14, like that. I think that's a valid move. Let me just double check though. Yeah. So a cell that is either to the bottom or to the right, not necessarily adjacent. So yeah, so I think you are allowed to make like a move like that, where you jump from 9 to 14, basically. Yeah. And so basically, the thing you have to recognize is like, so from here, I can jump to any cell, right? And then from like here, for example, I can jump to any of these cells. And the thing you have to recognize here is what your jumps do. Like, let's say I jump, like, so, well, actually, sorry, you can't make, you actually can't do what I said. So you can't do this. You can't jump from here. Sorry. You can't jump from here directly, but you can jump like from 5 to 6 or something. But notice what happens. So in this first example, they tell you the best thing is you start at cell 01, which is over here, and you go to this cell over here, this cell 14. But let's look at a couple ways we can get there, and we're gonna see that it doesn't really matter. So if we let's look at this path. Oh, not that path. Let's look at this path. So here, our score would be 7 minus 5 plus 14 minus 7, which is a score of 9, right? So is that the total? Yeah. Okay, so this is a score of 9. Now let's look at, maybe we won't go this way. Maybe instead we'll go 5 to 9 to 7 to 14. So if we do that, let's get rid of this. So let's go 5 to 9 to 7 to 14. So this will be 9 minus 5 plus 9 minus 7 plus, actually, sorry, this is 5 to 9. No, 5 to 9 to 7. Okay, so it'd be like this. And then to 14, so 14 minus 7. There we go. Okay, so 5 to 9, right? So that would be num2 minus num1. 9 to 7, so num2 minus num1, and 7 to 14. So what is this? This is 4 minus 2, which is 2, plus 7. So 9 as well. Now, let's say we go another way. Let's say we go 5 to 7 to 6 to 14. And this is the last one. And then I'll kind of show you why it doesn't matter how you get to the number. Like, as long as it's possible to get there, it doesn't matter the path you take. So this will be 7 minus 5 is the first jump. And then second jump is 6 minus 7. And the third jump is 14 minus 6. So here we also have 2, -1, which is, oh, maybe I did something wrong. No, I didn't. This is 1 plus 8, so 9 again. So notice if you actually look at this equation, like if I do a bunch of num2 minus num1, basically what I do is I do like num2 minus num1 plus another 1, right? But notice that whenever I take 2 jumps, this num1 is the old num2. So these are exactly the same, right? So when I take multiple jumps, like this 7 and this 7 is the same. And then this 6 and this 6 is the same. So if I actually cancel everything out, like here's a 7 here, a 7 here, a 6 here, and a 6 here, then you kind of notice it's basically just your total score is just last number minus first number. So it doesn't matter what path you take at all. All it matters is like what number do I start at, and I'm only going to want to make one jump essentially. So basically what I want to do is I want to make the jump that gives me the greatest profit, which in this case, I can go from 5 to 14. That gives me 9. That's the best. So in example 2, the best profit is just 2 to 1. They're all negative, but this is the least loss. So what you really want is for every square to know, like, what's the best square to get to the square from? Like, what's the smallest square in this, or not the small square, like for this square, if I take this entire square, where this is the bottom right corner, what's the best number to get here from? And that, I tried to actually calculate it using just like a traditional, just like a nested for loop, but it doesn't really work. Because in order to get what's the best square for here, there is no way to like traverse it where I have all, like, I can't just like maintain the smallest square I've seen so far, no matter which way I go. Because like for here, let's say I go row by row, then I'm going to have some squares that are invalid, like these squares are invalid. And if I go like column by column or something, maybe I'll go like this way, then I'll also have stuff that's invalid, right? I'll have like these that are invalid. So the better way to do that is actually DP. And it's a really simple DP, but essentially for this square, the smallest square in this whole thing is going to be either the smallest square in this whole, like if I have the result for this, or the smallest in this, or either one of these two squares. So let's kind of show you what I mean by that. So let's say we have a 4x4. I think we probably should. Here we go. So we have a 4x4. So initially what I'm going to say is the smallest square that you can get to all these squares from, I'll just make it -infinity, because that will represent no jumps, right? So like for all these squares, I want to say the smallest square that you can get to these from will just be, sorry, not -infinity, we'll make it infinity, because it's num2 minus num1. So we'll say these are all infinity. So infinity, I'll just do that. So these are all infinity, 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 infinity. Okay. Now, actually, sorry, that's not true. So the only square that's infinity is this. Okay, there we go. So this square will be infinity. These will not. These will only be infinity if you got here from the top. So when I calculate, like, what was my result from the top, that'll be infinity because there's nothing here. And these will be infinity when I got here from the left. So now let's walk through basically what happened. So for example, for this square, we're going to say this square, the smallest square that we can get here from is either the result to the left, which is infinity, or the result above, which is out of bounds, so we'll just default that to infinity as well, or the square above, which doesn't exist, or the square to the left. And the square to the left here is 9, so the best is 9. So we'll say 9 here. Let's get rid of this. Okay. And then similarly for this square, like this is infinity because it's out of bounds, and there's no square here. The square above has a value of infinity, and the square is just 9, so this is going to be 9. Yeah. Okay, now for this square, let's say. So for this square, it's either going to be the DP values of these two, which is 9 and 9, or the actual square, which is 5 and 8. So the smallest one there is 5. And then for this square, so we're going to speed it up a bit. So the dp value to the left is a 9. The actual value to the left is a 5. And the top two are out of bounds, so this is 5. Yeah. And this one, the dp value to the left is 5. The actual value of the square is 7. And the top two are out of bounds, so the best there is 5. And then, so you can kind of see, similarly here, the two dp values are 5. The squares are 6 and 9. So what's the smallest there? 5. And then here, the dp values are 5 and 5. The square above is 3, and this is 6, so the smallest is 3. And then here is going to be, so 9 or 8 or 2 out of bounds values, so 8. And then we'll do this one, so 8 or 6 or 2 out of bounds values, so 6. 5 or 8 or 9 or 6, so 5. 5 or 6 or 7 or 2, 2. And then here it's a 5 or 6 or 7, so 5. 1, 14, so obviously just 1. Let's see. Yeah, so 14, 5, 2, 5, 2. And this is going to be 2 as well. So once we get this, you can do this first. You can get this whole thing, or you can get it on the fly. But essentially now, you just go through all of these dp values, and these dp values represent, like, what's the small square I can get here from? And then it's pretty easy, right? So for every single square, you just say, like, okay, so give me this square value. So, like, for example, if I'm here, give me this square value, which is this value here. So 5 minus the small square I can get here from is 9. So the best result I can get if I end up at this square is -4. And basically, once you do that for every single square, the best one is going to be this square here because the value will be 14. And then the small square I can get here from is 5, and that will give you 9. So that's kind of what you do. You fill out this grid for a smallest square above or to the left of the square, and then you just get the actual value of it minus the smallest square that you calculated. And that's basically what I did here. So could have used like an array, so it looks a little weird, but essentially, yeah. So you just loop through and you just say, what's the top value? Either give me the dp value or the grid value above, or if it's out of bounds, just give me infinity. Same thing, what's the left value? Either give me the dp value or the grid value, or if it's out of bounds, give me infinity, and then give me the min of these two values, and then the result is the minimum of the actual value of the square minus the dp value. So I don't know why I called it cache, could have called it dp, but essentially that's basically it. Yeah. Right. And the last one, kind of hard. So in this one, you're given an array nums, which is a permutation of these things. So it's a little bit confusing. So basically, you're given an array that's a permutation of n numbers from 0 to n-1. So if you're given an array of like 4, it will be basically a permutation of 4 in any way. So it can be like 1, 2, 3, 0. It can be 0, 1, 2, 3, like whatever. Some kind of permutation of that. And the score of a permutation is defined as, and so here they kind of tell you. So once you're given the array, like let's say you're given this, you have to return a permutation. Let's say I want to give a permutation like this. And for this permutation, the score will be perm0. So perm0 is here, minus nums perm1. So it's going to be nums of 1. Plus perm1, which is this value here, minus nums perm2, which is nums of index 2, and so on. So let's kind of walk through the example to make this easier. So essentially, if we have 1, 0, 2 and 1, 0, 1, 2, so now the score will be the absolute value of, let's actually do a comment. Yeah, so this will basically be perm0, which is 0, minus nums perm1, which is nums of 1, which is 0, plus perms1, which is 1. I believe that's right? Let's see. Yeah. Minus nums perm2, which is, so nums of 2, which is 2. And then plus perm2, so that's 2. Minus nums perm0, so that's nums0, which is this over here, 1. And so kind of confusing, takes a little while to actually figure out what's going on, but basically this gives you 2. But essentially, the main thing for this is to recognize, starting off, that like if this is a solution, like let's say this is your solution permutation. As long as the order stays the same, it's going to give you the same exact score. So like this and this and this will all give you the same exact score. Yeah. Well, you can actually probably try, in fact, and I think it will pass. You can try every single starting value, to be honest. So you could say like, maybe I don't know this. Maybe I'll just try like a 1. But yeah, essentially these gives you the exact score because you're kind of just like looping through your permutation up to the start, right? So you're saying like, give me this value and this value. So basically it would be like, give me 1 and 2, then give me 2 and 0, then give me 0 and 1. And like, no matter what way I go through it, I'm always going to get that, right? 1 and 2, 2 and 0, 0 and 1. It'll just be in a different order, but because it's addition, like the order doesn't matter. So essentially from here, you know that like the start of your permutation can just be a 0 always, because no matter what it is, you can always just start with 0. Like if it was like 3, 2, 1, 0, you can say that's equivalent to the same thing as just this rotated around. So like 0, 3, 2, 1. It would be the exact same thing. So hopefully that makes sense. I think you can still pass without doing that though. But so basically, now that you know that, now that you know that your permutation starts with 0, now you're basically just kind of doing like the constraints are small enough where that's all you need to know, and you're basically just brute force DPing every combination you can. So essentially, you say like, okay, well, if I put a 0 here, what information do I need to retain? Like how do I know what number to go with next? So that number, because there's only 14 numbers, you can just use a bit mask. So you can just have a bit mask of like, let's say I have 5 numbers, I'll just have like 5 zeros. And then I'll say like, I'll start with a 0, so this will be on. And then for the rest of them, you basically just turn them on when you use them. And then when the whole thing is 1, that means you're done. So if you've used every number, then you basically need to calculate this thing right here. So that's the other thing, is like when you use a number, like what do you need to know? Like let's say I used this before, but now I choose to pick like a 1. Well, I actually need to, like the way this is gonna work in DP. So I used perm 0, but I didn't actually calculate the score yet. But now I picked perm 1. So in order to calculate this, I need to know what I actually picked for 0, right? So basically like, okay, I'll start with a 0, and then for my second number, whatever I pick, let's say I pick a 1, to calculate this, I actually need to know what was my 0th value. So you can just keep track of a bit mask of numbers that are available and the last number you used. And then from that information, you can just say like, okay, well, if I use a 1 and my last number was a 0, then I know how to calculate this thingy. And then also when I use every single number, then I have to do this one as well, because I haven't done that yet. So when I use every single number, then this is going to be the last number I picked. So perm n minus 1 is going to be the last number I picked. And then this, we know that perm 0 will always be 0, right? Or like I said, you can loop 14 starting numbers. That'll probably work as well, and just write it down. That would be fine. But essentially, so let's walk through it. So all used means every number was used, which means like, let's say if I have 5 numbers, my bit mask looks like this now, because everything is like turned on. And so now let's look at the actual like DP function. So essentially, if I used every number, then I need to calculate this thing, which is just, so the last is the last number I used, which I'll have in here. And then this is just, last is this number here. And then I need to calculate this. So this is nums 0, because my permutation will always start with 0. And what I'm going to do is I'm going to return the minimum like score along with, so I'm going to return a tuple of the minimum score along with the actual permutation, because you need the actual permutation. And I'm going to like combine the permutation as I go. So as my base case, I will just return the last number used, and then I will just keep adding on to it, and I'll kind of show you how that goes. So we make our result infinity, we make our best permutation an empty array. And then we just loop for every single number from 1 to n, and we check, is that number available? A bunch of ways you can do this, but essentially, if our mask ended with 1 shifted some bits to go to the index of that number is 0, that basically means like let's say our mask is like this, and we AND it with this. So this will give us a 1, or not a 1, it'll give us a non-zero number. But if the bit was off, then it would give us a 0. So that's one way to check if the bit's off. So if the bit's off, then you just do a DP where you get the new mask, and then the last number is used as the I you picked. And then you just and then you also add like the actual value of, like, if I picked this number, right, I need to calculate this. So like, let's say I picked this number here, then I need to calculate this. So that's that here. The last number I used minus nums of the current number. And then if the current result is better, so this is the other thing is, so they tell you return the lexicographically smallest thing. Easiest way to do these is, that kind of takes care of this for you, is to just make sure you loop in an alphabetical order. So basically, like, let's say I put in a 0 here. Just like, if you loop from 1 to 14 of the numbers you try, right, only change your answer if your answer is actually smaller than what you had before. That way you're kind of looping in a lexicographical order already, and if you have a tie, just keep the one you had before. So that kind of takes care of that. Yeah, so basically if we have something smaller, then we just take the current permutation, and we, like, the permutation that we got from the DP, and we update it, we update our result. And then finally, whatever permutation we had, that's after we picked our number, right? So from this state, like, let's say we already picked 0, and now we have like 0, 1, 2, we have like 1, 2, 3 left. So after we pick something here, we'll have our DP will only return us 2 numbers, so maybe like 2, 3. So this 0 we picked before we even got here. So let's say we got to this after we picked the 0. So essentially the DP will return 2, 3, and then we also need to add the number that we currently picked, which is always going to be last, because last is going to be like the last number picked. So that's the one we need to add to the permutation. Yeah. So that'll basically just be that. So essentially we're kind of adding a number to the permutation, not right when we pick it, but like right after we pick it, if that makes sense. So like at index 0, we actually won't add it to the permutation. We'll just leave it. And then when we get to this, then we'll add it to the permutation. But essentially you just keep adding your last number to the best permutation you found. And then this DP function is going to return the smallest score and the permutation, and you just return that. So for a 7-point problem, definitely quite doable. As long as you recognize you can basically just brute force DP. And yeah, so let's go through the time and space and all that for all these really quickly. So this one, pretty easy. I'd say this is just O of 1, O of 1, because a string is only 26 characters. You can say O of 26 if you want to. Either one's fine. Let's see. This one, like I said, is O of n. So time O of n. Space O of n is just Cadane starting at different locations. Okay. This one, so this is n by m, because essentially we're just calculating for every cell. All we're looking is the two right next to it. So that happens in constant time. And then we do have the what's it called, the dictionary. We can also use like an array and probably make it faster, but whatever. I just wanted to make it work. So this is n by m space as well. All right. So this one, the bit mask. So bit mask has 14 bits here, or whatever n is. So this bit mask can have 2 to the n states. So basically, like if a bit mask has n bits, each bit can be on or off. So that's 2 to the n. The last number can be any one of n, so that's n. And we loop from 1 to n as well, so that's n again, so n squared. And then our space is 2 to the n for the mask, and the last can be n. So it's like this. Yeah. So yeah, this is definitely a contest that could be solvable. I'll probably post the bi-weekly one eventually. I did the first 3 problems really quickly. The last one's kind of hard, so I'm going to try to spend a decent amount of time on it if I have time for that. So if I do that, I'll post it as well. But yeah, thanks for watching. Hopefully this was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one.